Hello, my name is Simon Andersen, and I will be presenting some neural networks that I've been doing in conjunction with FPGAs and how I've done these. In this video, I will be presenting a bit of who I am. I will be presenting my bachelor's project with an introduction and some hardware that I've made in it. And then my master's thesis with an introduction, something about the RISC-V processor that I used, the hardware implementation, and the fact that I used Chisel for describing the hardware, where Chisel is a hardware description language which can generate Verilog. So who am I? I just recently graduated from the Technical University of Denmark, where I have a bachelor in electrical engineering and now a master in computer science and engineering. And I really recently started working for a company called Teledyne Reason in Denmark. So first I will be presenting my bachelor's project. And in this I have made an hardware accelerator for image processing using an FPGA. The project went on some convolutional neural networks, how to implement these in FPGAs. In this convolutional neural network, I tried to detect or do MNIST classification. It was a static runtime implementation, meaning that it could only run one network in the finished design, but it was dynamic at synthesis time, meaning that I could do different sizes for it or different weights for it, and then synthesize a new network that would be able to, or a new FPGA build for it that could then run this network. This is all open access and can be found on this link here, the report for it. So my network configuration was based on convolutions, max pooling, and a fully connected layer at the end. And this is just to show what I was working from. So you see we have a convolution layer, a max pooling layer, convolution layer, a max pooling layer again, and then a fully connected in the end, which gives us the results. So we have 10 outputs in the end because we have 10 numbers we want to be able to recognize. And we start with a 28 by 28 input image of RGB. So the hardware for the bachelors was can be seen here. We have some inputs and outputs, and then we used a double RAM implementation where we have one RAM, which is a top RAM 0 here, is used for loading the neurons, and the other one is used for storing the neurons. And then when one layer has been processed, we swap them over and load from the opposite RAM and save to that. Other than that, we have a number of Magpul filters, which are the ones doing the actual computations. And then a max pooling because this is done most of the time, so that is implemented in the same layer. And as we can see here, it's been made in a pipeline fashion, so it's easy to add pipelines to the system and improve the performance in that way. Um, so when it's important to do parallelization when we're doing hardware on FPGAs and doing calculations, because this is a way we achieve fast computations compared to a processor which can run at gigahertz, where our FPGA is stuck at a several hundred megahertz instead. So what we do here is we use a number of DSP blocks, so we can do multiplications and additions with these, and we have them in a hierarchical fashion. So we do all the multiplications in parallel for 25 weights because our convolutions are 5 by 5, which gives us 25 inputs, and the same with the neurons. So we have 25 multiplications in parallel, which are then added up in a tree to give a single result. The logic for itself, for a Magpul filter, is here. We can see the Mag um, takes in 25 weights from a ROM, which is generated at synthesis time, and then 25 inputs of 16-bit wide. We then have a loop here that does a saturation check, and this is because when we're doing multiplications, we need to, or convolutions, we need to add up the result. So therefore, we either need to add it to itself, or if it's a new layer, we need to add a 0 to it. And finally, we do the ReLU operation here, which is the final part of it, which can also be controlled based on how you want to do the ReLU or if you want to do the ReLU. You also have the BIOS RAM, which is added at the end because that is added after a convolution is done. So the most important part of this project, or one of the most important parts, was the memory organization. And this is an image which is we can see here, which is 14 by 14 in this case. So in order to store that, we use this 5 by 5 configuration. So you can see each of these columns are one memory, or is one RAM. So we have a total of 25 RAM blocks, and then we stack each uh, multiplication that has, or convolution that has to be done on top of each other to obtain a smaller representation of it. This can be seen more in the report that's been written about it. Yeah, so the idea here is that in order to actually do a multiplication, we need to, or do a convolution, we need to extract all 25 neurons at the same time to do 25 simultaneous multiplications. So the first convolution will extract this one, and the next one will then go one to the right and extract that part and do the convolution again, and so on, and we'll store them. Um, Now we looked into the representation of the numbers, and to do this we looked at the weight distribution, and we can here see all the weights for our network that was run, and their values. So we can see that the vast majority of them are within around 0.1 to plus 0.1. While they extend all the way up to plus minus 0.6. But as we can see here, this is 1000, so these are very few. And then if we zoom in more, you can see here if we cut it down so we can reduce the number of bits in our fixed point representation, we don't lose that much information. And we don't remove the numbers as such, we just truncate them. So a 0.6 in this case would become, for instance, a 0.2. Um, yeah. And that was my bachelor's thesis, and you can look more into that in the report if you want to. So now for my master's thesis, which was a RISC-V based neural network processor for inference in hearing aids. This was based on RISC-V, the processing architecture. It was a system-on-chip implementation where we had a processor with a number of accelerators that could take inputs from the external system. So it's meant to be a full solution instead of just an accelerator for a part of a solution. It was done in Chisel, which is a hardware description language, which I will tease a bit here, but I will not go into the depths with it. And this is also open access and can be found the thesis itself, and all the code is also available on GitHub. So the motivation for this was to make a neural network, that neural networks can outperform conventional approaches for doing most engineering sciences nowadays. However, ultra-low power implementations, which is for instance a hearing aid, has certain limitations for this. You don't have as much space, and you are very power constrained on it. So these things need to be taken into consideration. The goal was to have a full system running a neural network. The exact neural network wasn't that important, just showing a system that can run a neural network. Because if we can run a neural network, we should be able to run more neural networks. And then I wanted to evaluate Chisel, this hardware description language, for larger designs to see how well it performs compared to VHDL or Verilog. And the starting point of this project was a baseline RISC-V processor and an idea of how to do it all. So the project itself was a RISC-V based neural network processor, where the neural network was looking into speech recognition, but it should be generic for other types of inputs as well. I've been using TensorFlow as a neural network library for it, and this is primarily due to the Light microcontroller library, which allows to export the network into a library which is based on C++ only for microcontrollers. So that removes a lot of the need for OS system calls and stuff like that, which helped a lot in the end. And finally, it should be a system on chip, so it should be able to handle the inputs, handle the outputs, and process the samples. So RISC-V, for any of you who don't really know it, is an instruction set architecture. It's a reduced instruction set computing processor. It is very extendable and allows for custom instructions. As you can see here, we have a number of extensions. We have a base integer instruction set where you can either choose the 32-bit, 64-bit, or 128 bits. And then you can add a number of extensions. Some of the extensions require other extensions, but you are almost free to mix and match them all as you want to. For instance, you will normally include the multiplication extension in most designs because that is quite useful for fixed point multiplication or integer multiplications. And the format is saved in a way that is quite generic. Now, what is Chisel? And Chisel is a hardware description language, which is like VHDL and Verilog. It is a library for Scala, and Scala is based on Java, which means that anything you can do in Scala, you can use in Chisel, and therefore anything you can use in Java, you can use in Scala, you can use in Chisel. So you can use for loops or if statements and all of this to generate your hardware using the Scala constructs. And Scala is also focused on functional programming, so you can use a lot of these tools to actually speed up how well you do or how fast you can make some new hardware. It's an object-oriented language, which is something else compared to VHDL and Verilog. System Verilog has some object-oriented approaches to it, but Scala is an actual object-oriented language. It uses something called Fertile, which is the flexible intermediate representation for RTL, where RTL is a register transfer level for the description of the actual circuit we're making. And this is used for synthesizing either the Verilog code that you can use in for your Altera or Quartus or Xilinx Vivado tools afterwards, or you can use it for simulations and stuff like that. So the neural network that I've made in this in my masters was, as I mentioned, speech recognition with trigger word detection. So it should be able to recognize one or more specific words from speech, such as yes, no, up, or Marvin, or whatever you say. And I looked into two datasets. One of them was the spoken Wikipedia Corpora dataset, which is 182 hours of aligned words. But after looking into it and trying to adjust it, I found that the quality was not as good as I wanted to. So to have a simpler dataset to begin with, I used the Google Speech Commands dataset, which is 65,000 utterances of 30 different words, such as yes, no, up, and Marvin. Was way more clear because all of them were 2 seconds long, and there was no noise in the samples, so you could find exactly where the talking was happening. So when working with neural networks, it's very important to consider pre-processing of it to allow your neural network to perform at its optimum instead of having to recalculate stuff and make it much more expensive. So one important thing is when we're looking at the audio, is the time domain versus the frequency domain. So this is the time domain representation of a person saying no, where we have the amplitude and the time on the x-axis. And this is very hard to see that it's somebody saying no. So what we can use instead is a frequency domain representation, such as a spectrogram, where we here have two different people saying no, and then I have drawn a contour around the high power parts of the spectrogram. So on the x-axis here we still have the time, and on y-axis we have the frequencies, and then the more yellow it is, the higher the power of that time and frequency is. So you can here see that two different people saying no look quite similar. We both have a little nose here, but we can also see that it's two different ways to say the word. And this is way easier for a neural network to actually process than this time domains is. So for the software implementation, as mentioned, I used RISC-V, and there are several tools readily available for this. For instance, the compiler, the RISC-V GNU toolchain, which has both a compiler and assembler for the C and C++ code, and then it also contains the GDB for a debugging environment. It also contains Spike, which is an instruction set simulator, or a golden model for how the processor should work at any given input, which are both freely available to mess around with and to use to test the system. I also used the TensorFlow Lite microcontroller because this can run neural networks, and it's written in C++. It has minimal change needed for porting to another system, such as my system on chip. I have it working in simulation and on FPGA, running a neural network from TensorFlow Lite on my system. There are multiple examples for it, and it's also freely available to use. Other than that, I made some profiling tools to tell me where to add accelerators, because once you have a neural network, it will run for a long time. So profiling tells me exactly where the processor is spending most of its time. And this is convolutions when you're doing a convolutional neural network. So here we have two examples, or two graphs showing my program running. And this is for the convolutions. So first, if we look at the functions, we can see here how many cycles are spent in each function. And this is the accumulated time in each function. So some of the functions are having quite a slow time, and then just at the end here, we can see that the last function and the last functions are the vast majority of the time spent overall. And then this is one function. We can see this is the last function here. It's around 250 instructions long, and we can see that the first 120 instructions are only done once. So this is setting up the function, while the next 100 instructions are the ones where the loop is happening. And we can see this top part is the most critical loop that is done. So that takes way more cycles than other ones. And it's important to mention here that this is a logarithmic scale. So this one takes a ton more time compared to this part of it. So for the hardware implementation, I started up with a processor, which is the RISC-V Mini, which is developed at Berkeley. It's a RV32i, which means that it's a 32-bit base integer instruction set. It's written completely in Chisel, and it contains a 3-stage pipeline. The reason why I went with this was that I worked for implementing it in a hearing aid where frequency isn't the most important part, but size and power consumption is. So when you're working with very small or when you have very high power constraints, you will often do smaller or lower frequencies to actually conserve the power. So therefore, it's better to perform more in parallel than it is to have higher frequency in your circuits. The system itself is based on memory arbitration, where here we can see an image of how I made the system. So we have the memory arbiter in the middle, which everything is connected to. We have, in this case, a single processor, which is the RISC-V Mini, which has two interfaces, one for the instruction and one for the data, because the RISC-V is based on or can do up to two data requests at a time, one for the instruction and one for the data. And it's a processor to all communication, which means that the processor can reach all of these units through the memory arbiter. The accelerators are also able to access the memories using these interfaces. So the MMIO is what the processor talks to, while the MEMIO is what the accelerator uses to talk to the memory. So that way our FFT unit here, which is used for instance for doing a spectrogram, can, instead of being given the data it needs to work on, go into the memory and read the data it needs itself. And this has been done in a way such that if the RISC-V or if the processor needs to look into the main memory, then the FFT can still read from the audio memory at the same time without limiting each other. But if they are requesting the same memory, then they will have to wait for the other one to finish. The peripherals can also access the memories, but as needed. For instance, our UART here has a MEMIO interface and an MMIO. So the MMIO is what's used for the processor to write to the UART's registers, and then the MEMIO can go in and read from whichever memory it needs to when needed. So I looked into some different implementations that could have been done, and one of them was using a network on chip instead. This would still be based on memory arbitration. It would have some all-to-all communication where we can see here the processor is able to talk to all the other units. We would have a ByteTorus function here, but that could be adjusted for the needs and how much bandwidth you need per between each processing, or between, for instance, the processor and the UART, or the processor and the RAM as needed. And all of them can talk to all of them or each other. The memories here are also stored as one as a component itself, but they could also have had local memories for the components, such that the ADC might have a small amount of RAM allocated to it on its side, which could then also be accessed using these routers and the network interfaces. And this works for both the accelerators and peripherals. In this case, I've shown them all, but to keep the NOC simple, you could also have taken multiple accelerators, for instance, the 7 segment and the GPIO, and joined them such that you only have to write to one set of registers there when they're not critical, when they don't need that much bandwidth. A third way of doing it was using memory divisions, which is also based on memory arbitration. It's more of a scratchpad principle where we access and use memory, and then we can pass it on to whoever else needs it. This allows for some simple implementations or lean on resources, so we only use a minimal amount of resources. We don't have a lot of arbitration because this would be up to the processor to tell which component is allowed to use any given memory at a time, such that one component at a time will request one memory. And by doing that, we can OR together all the request signals for each memory, which gives a way simpler arbitration scheme. But again, if, for instance, both the ADC and the FFT requested from memory 0, that would mean that the address and data bits would be OR together, so you'd get the OR result from the ADC and the FFT, which you do not need or want. So this is a good implementation for when you need fast access and can do in a scratchpad fashion of it. So the chisel implementation of it all. I'll here show some code examples just to show what chisel can do and how I made it, to show why it's better than, for instance, VHDL or Verilog in this case. So the system is, as I mentioned, based on memory arbitration. Everything connects to the memory arbiter, and then a loop handles the connections. So this is the memory arbiter FPGA described. You don't really have to know what all of it means, but the idea is that we have the I/O, which is the ports, and then we have the I-cache, D-cache, which are these two ports here. Then we have the MMIOs, which is a vector, so an array of MMIOs. So this is each of these we can see here are then stored in that. Then we have the memory links, which are the MEMIOs of these. And then finally the memories, which is on the right side here. So that are these MEMIOs. So in order to add stuff, we can just do it in a loop. And then when describing, for instance, a memory, I have here a module which is a memory, my memory, which is 256 kilobytes in size. And then some audio samples, a boot ROM text, and a boot ROM for data, just as we have up here. And the good thing about Scala is, again, we have the print line. So for instance, here I print the start address and end address of the boot ROM to my console when I am synthesizing the design or compiling the design to show just what the values are. And then the end, I have the memories here where I have a sequence of these memIOs, and then I connect each of these four to the memories, and that's all I need. So if I needed another block or another audio sample memory, I would just copy this line, and then I would take the other name for that and then add that to here, and then I would have a new or an extra memory into it. The system is also for the peripherals are done in the same way. Again, we have some code here that's not really important, but the idea here is that when I define a peripheral, I define that it has a pin I/O, and the pin I/O is these ports that goes to the externally to the system. And then I say that it's an MMIO module, which means that because it extends the MMIO module and has with pin I/O, then I need to define number of bytes, MMIO, pins, module name, to actually make it compile. So I say to the outside world that I have these vals defined. Furthermore, I have here the LEDs and the output, which is which is also used for the system itself. And then I here define a complete GPIO. So again, this is a chisel way of describing it, where we have the pins, so the pins to the outside world, which is this GPIO I/O. The LEDs of it should be connected to the LEDs that we define internally. The MMIO, we have the response, we have the bits, and then we have the data. It should be the output, and the valid should be the next of the request valid. Because that way we have here a pipeline for it. So regnext means that we take this value and then the next clock cycle. And then this, when my MMIO requested valid, we take a switch, which is sort of a multiplexer as well, just as you know it from both VHDL and Verilog. And then if this is 0, then if the address is 0, then we need to be writing to the LEDs and the output. So the answer back to the processor would need to be the LEDs. But if the address is 4, then we give the request or the answer back to the processor, the pins, the value of the pins concatenated together. For accelerators, we use this memlink to make them have the access to the memories. So we see that it also extends the MMIO module, but now it has with memlink instead. So it needs to have the module name, the number of bytes, the MMIO, which is a port for it, and then the memlink, which is the port for the memory. And then we can here see that we connect everything again quite simply, where we have our FFT is a module of a single FFT, which can then have these arguments for how large it is, and how many bits, and the fixed point representation for it. Again, you can see more about this in the report if you're interested. So the idea of the system is that it is easily extendable. Instead of having to describe a new port each time, you can show here the peripherals that I defined. All of these are done. I have the 7-segment module of a 7-segment MMIO. Give it the address and the name here, and then I say the I/O, the external 7-segment I/O should be connected to this module's 7-segment pins. And the same way I do for the SPI, the UART, the XADC, ADC, and GPIO. So I give each of them an address, and I can give them more arguments if I want to. And the accelerators, in this case the FFT, I have a module which I also give an address for the processor to be able to talk to it. And then all of the modules here that contains an MMIO module, I write up into this list. And all of them containing an MMIO, I write up to this list. And then there's a loop that handles the rest of it. So if I wanted another FFT unit, I would copy this line, call it FFT2 equals module something 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 with another address. and then add FFT2 in this list and FFT2.memlink in this list. And then I would, by that, have an entirely new accelerator. So that was all for my presentation. It was a brief overview of what I've done here. And you can find more information about it and all the source code for it. So the report for the Bachelors Project can be found through this link. And Bachelor hardware is VHDL written for my Bachelor. And the Bachelor here is a C# source code for emulating the neural network in software to have a reference point. For my master thesis, you can again find the thesis here on this link. And RISC-V Mini is all the hardware that I've done, what I talked to you about. So all the code you've seen comes from this repository. And trigger word is my actual is the neural network that I've been training to do the trigger word detection. Thank you for listening.